Hello everyone, my name is Huang. Today I would like to present my research study for the investigation of the effect of the colloidal nanosilica on the carbonation of concrete. So here in this page we have the so in this page shows the content of today's presentation, and I will start from the background and motivation. So as we all know, the cement industry is responsible for around 8% of the carbon dioxide emission in the United States. And a lot of different strategies have been proposed. And for example, one of the recent ones is the use of the PLC cement, limestone cement. So basically, people replace 10% of the cement by the limestone to reduce the emission of the carbon dioxide at the stage of the production, cement production. So we were thinking if that's possible, we can further reduce the emission of the carbon dioxide, or we can contribute to the carbon neutralization when the concrete is hardened. So we think about the concept of the carbonation. So carbonation is a well-studied topic. It's the reaction between the cementitious material with the carbon dioxide. So for example, over here shows the reaction between the calcium hydroxide, the CSH gel, and other component in this concrete with the carbon dioxide. And based on our literature review, the carbonation process sometimes can be damaged and sometimes can be good. So we were thinking maybe we add some nanomaterial, maybe we can improve some of the properties to compensate the loss of the, for example, this other properties of the concrete because of the carbonation. So we choose the colloidal nanosilica. This material can gel immediately when in contact with the alkaline environment, for example, the cement pore solution. And it will form a 3D physical network inside the entire system. So this network can potentially slow down the diffusion of the water or ions in the concrete systems. So based on our previous study, as you can see on the right, the figure shows the increase of the water retention capacity of the cement paste. So in simple words, the water is difficult to be released or evaporate inside the concrete system when there is a CNS. Regarding to the carbonation of the nanosilica, we did a literature review, and this table shows part of the paper that we review. And as you can see, a lot of study has been done, and we found out that for the most of the study, they use powder form nanosilica, and the result indicates an increase in the carbonation resistance. So that means less carbonation absorption. And it's also interesting to find that for the very few paper they're using, for example, suspension nanosilica or the colloidal nanosilica, they found some level of the decrease in the carbonation resistance. So that means more carbon dioxide absorption. Still, we believe there's a very limited research related to the carbonation of the concrete using colloidal nanosilica. And that's the reason we conduct this study. The literature review also shows us there are many different factors that can change the intensity of the carbonation process. For example, transport properties, degree of saturation, volume of cement, or the hydration degree. And based on that, we designed 6 different experiments as our preliminary investigation. And I will start from the quality of the interface, and this is very related to the transport property of the concrete material, since there are many interfaces in the infill application of the concrete. And what we did was design a double layer paste sample and did a micro CT scanning. As you can see on the right, we have a base layer and then variable layers. So for the base layer, they are all the same for the different samples. They are just the cement paste. For the variable layers, we add the nanosilica, and we have the reference sample without any nanosilica. So as you can see in these 2 videos, for the left is a reference sample. We can clearly observe the interface in between. So However, when we have CNS, the interface was kind of disappeared. But of course, it's not disappeared. Of course we have an interface, but it's just porosity was reduced, the connectivity of the interface was reduced, and it's not showed. It's much better than the reference. And we believe that this was due to the pore refinement and improved particle packing induced by the colloidal nanosilica. And now, if we have a better interface, theoretically, we should reduce the permeability of the concrete sample. So in this work, tells us the carbonation, the penetration of the carbon dioxide should be reduced. And then we move on to the internal humidity, because the saturation of the concrete sample is also important. It related to the carbonation intensity. And what we did is we designed 4x8 concrete cylinder with embedded humidity sensor. So the result indicates with like 0.3 or 0.6 or even 1% of the colloidal nanosilica, we can increase or maintain the internal humidity, and it was higher than the reference sample without any CNS. So it's 5% higher. And what we believe is that when we have this kind of colloidal nanosilica, as we mentioned before, we can the nanosilica will form a physical network inside the concrete system when in contact with porous solution. So this network slows down the diffusion of the ions of the water and reduce the evaporation and release of the water. So that's why we have a higher internal humidity even after 30 or 40 days and even longer. And as on the right, the water retention capacity was also higher. So in this study, if we have a higher internal humidity, it should favor the carbonation process, because we have more moisture inside the concrete system. And next, we will move on to the hydration performance of the influence of the CNS on the concrete. And what we did is, this was part of our previous work. We have prepared some sample, and then we preload and induce some damage to our sample. So as you can see at the beginning, after the preloading, we have cracks, and then after a couple cycles of the wet-dry condition, so just wet water, moisture cure, and then dry cure, just a couple cycles, the crack disappeared. And we compare it when we have CNS, or when we have 0.3, 6, and 1% of the CNS. The self-healing was not only about the self-sealing. It's not the close of the external cracks, but it also shows some recovery in the mechanical strength. In this case, it's the tensile strength. So we have higher tensile retention ratio when we have the CNS inside the concrete material. So we believe that this was due to the improved hydration and also the continuous hydration of the cement material. Also, for the mechanical performance, we test the strengths. Of course, we are not surprised to find the increase in the compressive strength when we have the nanomaterial, because you can also add as the nanofeeder, nano-seeding effect. It all contribute to the higher strength performance. And next, we test the porosity, because porosity is also one of the most important factors that can change the intensity of the carbonations. We did the MIP and rapid air image analysis method. So as you can see on the left, the result of the MIP indicates increase when we have the nanosilica. We can increase the portion of the small voids, and the large voids is reduced. So we kind of eliminate those large voids, but we increase the number of the small voids. On the right is the overall air content. As you can see, the air content was increased when we have the CNS. And this was kind of different from our previous literature review. And this is an ongoing study, and we look at the viscosity, the surface tension of the pore solution of the cement mixture when we have the CNS. It all shows some level of the change, and we are still working on it. Okay. And based on our micro CT scanning result, it also shows the same conclusion, that when we have the CNS, we can increase the overall porosity, but we eliminate the large voids, increase the small voids. Next is some preliminary result about the carbonation test for the cement paste. What we did is we prepared the cement paste and then ground them to the powder and then proceed to carbonation. And as you can see, we use 100% carbon dioxide concentration, and there's a 50 psi pressure for 24 hours. And then we chemically use the TGA and pH meter to test the change of the CH and the calcium carbonate content change. As you can see, before and after the TGA testing, of course, the calcium hydroxide content was reduced and the calcium carbonate content was increased. And if we compare it with the sample with CNS, the incorporation of the colloidal nanosilica increased the carbonation process. As you can see, the content of the calcium carbonate was higher. The increasing ratio was higher than the reference. However, it's also interesting to find the reduction in the calcium hydroxide was actually lower than the reference. So we believe that this was because the increase in the carbonation when we have CNS was not because of the carbonation of the calcium hydroxide, but it may be due to the carbonation of the CSH gel. And we did some review, and also we tried to find out why. Because CNS particle is a material that has negative charge on its surface. And previous researcher has pointed out this kind of negative charge on the surface has the potential to combine with positive charge ions. And in our case, calcium ions. So we believe that during the mixing, curing, even the carbonation process, those colloidal nanosilica negative charge surface may combine or extract the calcium ion from the CSH gel and make it more feasible for the carbonation process. Last but not least, we also evaluate the pH value to kind of verify our result. So I think it is the same with our previous observation. So for the sample with the CNS, we have a higher reduction in the pH value. So that means more carbonation. Okay. So still this study is still in the process. We also need to, so because I only did the TGA, so it's chemically evaluate the carbonation process. And we still need to do more. And one of my colleagues is going to present it this afternoon. It's he tests the other cement paste material, and he will introduce more. So as a quick summary, adding the CNS can enhance the quality of the curing, enhance the hydration, and based on our preliminary result, it increased the carbonation intensity. And we will need to do more about this. Okay, I would like to thank my advisor, Professor Lu, and also my lab colleagues. Thank you very much.